Thank you, Ian. You know that you've made it in your scientific community when your research becomes the subject of a Eurovision Song Contest entry.
Detection of these gravitational waves will usher in a new era for astronomy. Here's the moment when they announce the discovery.
We have detected gravitational waves. We did it.
So that was Moldova's entry to the Eurovision Song Contest in 2016. On the 11th of February 2016, we made the announcement to the world and to our fellow scientists outside of our collaboration that we believed that we had detected gravitational waves, a signal which came from the collision of two black holes. It was heralded as the scientific breakthrough of the century, and it was associated with two black holes, one 29 times the mass of the Sun, the other one 36 times the mass of the Sun. They were dancing around each other as that animation showed, and they collided and merged to form one single black hole, 62 times the mass of the Sun. That object, that collision happened 1.3 billion years ago. It took that time for the signal to travel through the cosmos and then travel through the Earth, just in time when we had turned on our upgraded detectors. Now this is a new type of astronomy. You might ask, well, how did we get here? When we think of astronomy, you think about pointing a telescope to the sky, or perhaps you think of professional astronomy as many countries teaming together to invest in the money to build these extremely large telescopes. This is the Very Large Telescope, VLT, built in Chile, and of course the famous Hubble Space Telescope. And then we see these beautiful images of the cosmos. This is from the Hubble Space Telescope, a galaxy which is deformed in its disk shape, obviously due to some collision with another galaxy in its past. And as we look at the universe, we think about looking at the universe in visible light. And so the central image there is the visible image of the Andromeda galaxy. But the visible light that we see with our eyes is only a small part of the light spectrum, what we call the electromagnetic spectrum. And when we look at the universe through different parts of the light spectrum, the universe looks quite different. So here you can see, as we move to the right towards X-rays, these are more energetic light that we're receiving from that galaxy. You see into the heart, the center of the Andromeda galaxy at the violent energetic events. But as you move to the left and eventually over to radial, it's less energetic light. And then you see the outer parts of that galaxy. And so what motivated our collaboration for many decades to try to detect gravitational waves is, well, what does the universe look like if we observe it in this new window? And as we think about the universe, well, what is the universe made up of? And you could simplify the universe as being made up of about 100 billion galaxies, each of which contain around 100 billion stars. And so if we want to think about what's out there, well, we've got to think about, well, what are stars? If you start with a relatively small star, like our Sun, then that star will go through its life, eventually exhaust its nuclear fuel, and end up going through a red giant phase and then a white dwarf. But if our Sun was larger, like many stars out there in the universe, in fact, once it exhausts the nuclear fuel inside its core, the core will collapse due to the gravitational pull, the gravitational attraction, and it will collapse down to something that even the atoms that make up our bodies can't withstand. It will collapse down to something called a neutron star. A neutron star is so dense that 1 teaspoon of a neutron star weighs 10 million tons. But if a star starts off even larger, then its core can be so heavy at the end of its life that even neutron material can't withstand the gravitational pull, and it will collapse down to something called a black hole, something that's so dense that even light can't escape. That's why it's called a black hole. And what you might not be aware is the sense of scale. So we're talking about objects which are heavier than the Sun, and yet a neutron star, which would be about 1.5 to 3 times the mass of our Sun, will be around 20 kilometers in its diameter. That means that if the center of a neutron star was placed here in Motherwell, the outer edge of the neutron star wouldn't even reach Glasgow, it would only reach Steps. And a black hole can be 3 times the mass of the Sun and heavier, it could be hundreds of millions of times the mass of the Sun. It will start off about half that size, but obviously it can be larger depending how much mass you put in there. And of course you might be interested in black holes, and perhaps you've seen movies like Interstellar. This is one of the images from Interstellar. What you might not realize is that the computer simulations that generated images of black holes like this came from our research collaboration. Not from me specifically, I'm an experimentalist, but some very clever software scientists in the US generated these images. And so we've talked a bit about gravitational waves, but I've not explained what they are. Obviously, it's related to gravity, so let's look at what gravity is. So Isaac Newton, when the apple fell on his head, this didn't actually happen, he just came up with a story to help illustrate gravity. He said, well, gravity is a force. The apple has some mass, the earth has some mass, and that effect creates a gravitational attraction between those two objects, causes the apple to fall to the ground. But Newton himself realised that it wasn't a terribly good explanation of gravity. It had some potential flaws when you extrapolate what that means for the universe. But it wasn't until Albert Einstein came along, he said, no, gravity is not a force, gravity is a geometry. Now at this point you might glaze over and think this person is talking complete bonkers, but although the mathematics is complex, Einstein gives us a very simple picture. And he says that mass, for example our sun, distorts the fabric of space, a bit like a mass would distort a rubber sheet. And the Earth orbits around the sun, not because of an invisible force, but because the Earth follows the natural curvature of space. And this theory predicts the existence of gravitational waves. So our sun just sits there not doing anything, but many objects in our universe actually are moving around, accelerating. And so if you had two compact objects, heavy stars, orbiting around each other as shown here, you can imagine you get ripples in this fabric of space-time. So think of ripples in a pond. And these ripples are what we call gravitational waves, and we define a gravitational wave as a strain in space. That might sound weird. All I'm saying is it's a stretching and squeezing of space. I'm going to use one equation, please forgive me. The definition of a strain is a relative change in space. We define that as delta L over L. You calculate from Einstein's equations what you'd expect to see from two heavy objects, so this object's heavier than the sun, colliding in the universe. You end up with a number of 10 to the power minus 21. That's 0.2001. Okay, so let's think. If you have a 1 meter stick in front of you, that means that if a gravitational wave passes through us sitting here, then the ends of that meter stick are moving by 0.2001 meters. But it's a proportional effect, so let's make life easy for ourselves. And we build a kilometer stick, and we try to measure the ends of that stick. Well, that means they're going to be moving by 10 to the minus 18 meters, so 0.1701 meters. If you then compare that to a subatomic particle, like a proton, that's 1,000 times smaller than a subatomic particle. It's 1,000,000 times smaller than an atom. Compare that to the width of a human hair. Well, a human hair is just astronomical compared to the signal we're trying to see. Einstein saw these numbers. He said, it's impossible. You will never measure this effect on Earth. But thanks to the invention of some technology, particularly lasers, we can use a technique called laser interferometry. We use a laser, put it through a mirror at 45 degrees, split the light in half, reflect off these end mirrors, and reflect the light back. And because light is a wave, then there's a wave pattern in that light. And if you look at how those waves recombine when they come back out of this instrument, then those waves can either add up, that the peaks line up with the troughs, and it cancels. And then if something moves the mirrors, then it causes those relative position of those waves to move. And then if the peaks line up with the peaks, you get a bright output. And basically this is a technique that we can use the wavelength of light to be our meter stick to measure the position of mirrors, which in our case are separated by 4 kilometers. So there's an international network of these detectors around the world. There's these two over on the left-hand side, LIGO detectors. You might see that I'm advertising them here today. These are 4-kilometer laser interferometers built in the US, but with huge contribution from the UK, both in terms of the research and financial. There's a UK-German detector in Hanover in Germany. There's a nice 3-kilometer detector just south of Pisa, built by the French, Italian and Netherlands consortium. There's a planned detector in India that the UK is supporting the building of just now. And there's a detector being built, or has been built, under the Kamioka mountain in Japan. And so on the 11th of February 2016, we saw this signal. There's 2 traces of the signal from the 2 detectors which we had shown here. And there was a very formal press release in Washington, DC. There was a slightly more fun press release over in Glasgow, where as soon as we could, we cracked open the champagne and we celebrated the detection of gravitational waves. But these signals, as you can see here, perhaps saying that we're observing the universe in a new way is not the best way to describe it. Perhaps we should say that we're listening to the universe in a new way. And I could take the signal from our detectors with some very, very minor filtering and play it through the speakers in this hall. Do you want to hear what 2 black holes sound like when they collide? This is what it sounds like. It will play in the original pitch, which is very low frequency, then it will play phase shifted so you can hear it a little bit easier. This is the exact sound of the mirrors being moved in our detectors due to two black holes colliding. So that was really exciting for us. Okay, I promised one equation, but this is one plot from the paper which described that first detection. The paper was published on the 11th of February. Almost immediately after we published the paper, the journal's website completely collapsed due to the number of hits on that. And we counted that on that day, there were 961 newspapers which carried this story as the main front page story. It was very exciting for us, and it clearly was exciting to the wider public. This plot, if you look at the there's an artist's impression of the two black holes colliding, then there's the signal which we see, which is the middle trace. The bottom two curves, the black one represents the distance between the two black holes. As you follow over to the right, the distance goes to 0 because they've collided and merged. But the green trace, represents the relative speed of those two black holes. And the point where they merged, if you can read that plot, I'll tell you what the number is. The relative speed of those two black holes was 0.6 times c. c is the speed of light. The speed of light is 300 million meters per second. So again, think about objects which are 30 times the mass of the sun being flung around each other at a speed of 300 million meters per second. And so this was a big deal for various reasons. I've cited some reasons here. There's another simulation showing these two black holes colliding. It was the final prediction from Einstein's theories, which had yet to be directly observed, these gravitational waves, ripples in the fabric of space and time. It was the first observation of a black hole. As I mentioned, black holes are so dense even light can't escape. The only way to observe them is through gravitational waves. We did that for the first time. And also the first observation of two black holes colliding. But perhaps the most important thing, as I've probably been hinting at in my talk, is that this is an entirely new way to observe the universe. And that was why it received so much media attention. Here in the animation it's slowed down, and you can see the point at which these two black holes merge and form a single black hole. The event horizons then merge, becomes one black hole. So let's do a quick maths test. So we have two black holes. One is 36 times the mass of the sun, the other is 29 times the mass of the sun. 36 plus 29 equals what? So, hands up if you think the universe obeys the same mathematics that we were taught at school. You think maybe not. Well, it turns out that it's actually not wrong, that 3 times the mass of the sun, in a fraction of a second, was annihilated and converted into energy. Energy in the form of gravitational waves. So basically, 3 times the mass of the sun was converted into energy associated with the stretching and squeezing of space. Very bizarre thing to think about, but you can convert 3 times the mass of the sun into the equivalent power output, and at the point that these two black holes collided, the energy associated with that event was 50 times more than the equivalent light power from all of the stars in all of the galaxies in all of the known universe. So a very, very energetic event. You might ask, well, why did it take 1,000 scientists so many decades to detect the signal? But I don't have time to explain why that is the case. This gave rise to the Nobel Prize in 2017 for physics to 3 of our colleagues, Ray Weiss, Barry Barish and Kip Thorne. That slide there is Ray Weiss giving his Nobel Prize acceptance speech. The middle pictures are all Glasgow University researchers. So cited in that talk was a massive contribution from Scotland, and my PhD supervisor, later became also my wife's PhD supervisor, got knighted, Professor Sir Jim Huff. Great Scottish contribution to that work. And around the time the Nobel Prize was awarded, we saw another signal, 2 neutron stars colliding. And neutron stars are different from black holes because you can see light from those objects. And so not only did we observe this object in gravitational waves, we observed it with ground-based optical telescopes, radio telescopes with neutrinos, and in space we detected high-energy gamma rays. And so this became the largest astronomy study ever conducted by mankind. And all of those elements in the periodic table, I don't know if you're familiar with the periodic table, those are all the elements that make up the universe. All of those which have got a yellow colour on them, we now know are created in neutron star collisions. So one of those elements is gold, so if any of you are wearing any gold on you, you can look at it and say that originated, almost certainly, from the best of our knowledge, from 2 neutron stars colliding sometime in the past. And as shown here, I'm sorry, it's going to be just 1 minute more. We build gravitational wave detectors on the ground, but just like optical telescopes, it's useful to put detectors on the ground and detectors in space. And the next video is from the European Space Agency showing the future of the field and placing a detector in space. Thank you very much for your attention.